Section: Introduction. In this section, we discuss how transformer-based large language models, LLMs, despite their proficiency in understanding language, face limitations in processing large amounts of text at once. These models have a set limit on the amount of text they can consider in a single instance, known as the context length limitation. Moreover, their performance tends to drop when dealing with long texts, even if these texts don't exceed the set context limit. This is in stark contrast to humans, who can read, understand, and reason over extensive texts, such as interconnected series of books, with relative ease. We believe this difference stems from the distinct ways in which humans and LLMs approach reading. LLMs process text in a linear, word-by-word manner, which is quite passive. Humans, on the other hand, engage with text in a more dynamic way. We tend to quickly forget the exact wording of what we've read but retain a general understanding or the gist of the information for a longer period. Additionally, when we need specific details to perform a task, such as answering a question, we actively search for this information in the text. We argue that this ability to remember the gist of the text and to look up specific details as needed allows humans to efficiently process and comprehend long texts. For instance, to understand a character's motive in a novel, we often need to recall the overall storyline and the character's traits, which requires processing the entire book, not just the immediate context. Inspired by these observations, we introduce Read Agent, a system designed to handle long texts in a manner akin to human reading strategies. Read Agent is straightforward to implement using an existing LLM and operates in three main steps. First, it divides the text into manageable segments, or episodes, at natural pause points. Next, it summarizes these segments into shorter gists, keeping track of their origins. Finally, when faced with a specific task, Read Agent reviews these gists and decides which original text segments to revisit for additional details, thereby solving the task. We evaluated Read Agent's performance on several long document comprehension tasks and found that it significantly outperforms traditional methods that rely solely on gist memory, full text, or retrieval-based approaches. Specifically, on the narrative QA Gutenberg test set, Read Agent improved performance metrics by notable margins and effectively increased the context length it could handle by approximately 20 times. Similarly, on the quality dataset, Read Agent managed to triple the effective context length compared to using the full text. We also successfully adapted Read Agent for web navigation, showcasing its versatility and potential in handling very long contexts. Our primary contributions through this work are the development of Read Agent, a human-inspired LLM agent that leverages gist memory and targeted lookups to efficiently process long texts, and a comprehensive evaluation demonstrating its superior performance and scalability on challenging benchmarks. This approach not only enhances the effective context length that LLMs can handle but also reduces the impact of distracting information, all without requiring changes to the model architecture or additional training. Section Summary. In this section, we introduce the challenge of limited context understanding in transformer-based large language models, LLMs, despite their language capabilities. While humans can reason over long texts efficiently by focusing on gist information and interactive reading, LLMs struggle with performance degradation and distractions from lengthy inputs. To bridge this gap, we propose Read Agent, a system inspired by human reading approaches, which segments text into episodes, compresses them into gists, and enables interactive lookup for improved comprehension over long contexts, outperforming baselines in various comprehension tasks. Section: Retrieval. In this section, we discuss how we've developed a method to enhance the way language models, LLMs, can access and use information from large texts or databases. This method is known as Retrieval Augmented Generation, RAG, techniques, which essentially allow an LLM to pull relevant information from a vast collection of documents or pieces of documents when needed. Our unique twist on this involves using what we call a contextualized gist memory. This means we enable the LLM to understand and decide which pieces of information to retrieve based on a condensed version of the documents, all without needing any specific instructions for each task, a method we refer to as zero-shot LLM prompting. Our approach is particularly effective when dealing with long, interconnected pieces of text, like a series of books or extensive conversation histories. However, there's a limitation to how much information we can work with at once because the size of our gist memory is tied to the LLM's capacity to handle context. In simpler terms, the larger the database, the harder it is for our method to manage, unlike traditional retrieval methods that can handle much larger databases. In our work, we compare our method to other retrieval systems that use the same set of documents to see how well ours performs. We also explore how LLMs can act as agents to manage very long texts. Some systems, like WebGPT and WebShop, have shown that LLMs can search the internet for answers or learn browsing actions, even though they weren't specifically designed for understanding lengthy documents. Another system, Pearl, suggests action plans for better comprehension of long documents through repeated prompting. Similarly, a method called SelfNote improves reasoning by mixing in notes among the original documents. However, these methods struggle with texts that are longer than what the LLM can process in one go. MemWalker, a system related to our work, also reads long documents by prompting the LLM repeatedly and navigating through summaries of different levels to find task-related information. Yet, its structure of hierarchical summaries can make it challenging to connect related information across different parts of the text. Now, let's talk about ReadAgent, which is our system designed to tackle these challenges. ReadAgent uses what we call a gist memory, a structured collection of brief summaries or gists of text chunks from the original, lengthy context. Creating this gist memory involves two steps: dividing the text into manageable parts, which we call episode pagination, and then summarizing these parts into gists, a process we refer to as memory gisting. During episode pagination, ReadAgent goes through the long text and decides where to pause and create a memory episode, essentially breaking the text into pages based on natural stopping points between paragraphs. We use a specific prompt to help the LLM decide where these pauses should be, ensuring each page has a minimum amount of words. For memory gisting, we then ask the LLM to condense the content of each page into a gist. We emphasize the word shorten in our prompts because it helps maintain the narrative flow when we concatenate all gists to form the gist memory. The size of the original text chunk plays a role in how much we can compress the information without losing important details. Finally, we discuss two strategies for ReadAgent to look up information from the original text in addition to using its gist memory: parallel and sequential interactive lookup. In the parallel approach, ReadAgent looks up all relevant pages at once, while in the sequential approach, it looks up one page at a time, depending on the task at hand. Section Summary. In this section, we introduce Retrieval Augmented Generation, RAG, techniques that enable a language model, LLM, to retrieve task-relevant information from a database by reasoning over a contextualized gist memory, without explicit prompts. This approach leverages the LLM's language understanding capabilities to decide which documents to retrieve, suitable for densely correlated long document pieces, although limited by the gist memory size correlated with the database. Additionally, ReadAgent, a system discussed here, utilizes gist memory to interactively handle long texts by paginating content into memory episodes and summarizing them, allowing for parallel or sequential lookup of relevant details during a given task. Section: ReadAgent P. In this section, we discuss how we've designed a system to help our model read and understand long documents more efficiently. We start by explaining a method where we limit the number of pages the model can look at, but we also make sure it uses as few pages as necessary. This helps to avoid overloading the model with too much information and keeps computational costs down. We introduce an example where the model can ask for several pages at once based on a single question. This method allows us to update the model's memory with the main points from these pages, ensuring the story or argument flows smoothly. Then, we ask the model to tackle the task again with this refreshed memory. We also explore a different approach where the model looks at one page at a time, up to a certain limit. This sequential method lets the model build on the information it has already seen, potentially leading to better understanding and answers. However, this can be more demanding in terms of computation, so we recommend using it only when it clearly benefits the task at hand. When it comes to the computational demands and scalability of our system, we've found that the extra steps involved, like breaking the document into manageable pieces, summarizing these pieces, and retrieving specific information, do add some overhead. But, importantly, this overhead grows in a controlled, linear way with the length of the document. For example, our method for dividing the document ensures that the model doesn't have to process the document more times than necessary. Similarly, summarizing and retrieving information are designed to be efficient, so the model doesn't get bogged down by the details. We also talk about different versions of our reading assistant, which could be useful for various tasks, including navigating web content. In our experiments, we test our system on 3 challenging tasks that require understanding long documents. We didn't train our model specifically for these tasks to avoid making it too specialized. Instead, we used a general-purpose model and focused on how our system could improve its performance. We mainly used a model called PaLM-2L for these tests, but we also share results from another model for comparison. One key measure we looked at was how much our system could compress the information without losing the important points. This compression rate shows how efficiently our system can summarize long documents. Lastly, we evaluated our system's answers using both automated methods and human judgment. We designed 2 types of tests, one strict and one more forgiving, to see if the model's answers matched the reference answers either exactly or closely. This helped us understand how well our system could produce accurate and relevant responses. In summary, we've developed and tested a system that helps models read and understand long documents more effectively, which could be a valuable tool for many different tasks. Section Summary. In this section, we explore different strategies for long document reading comprehension, such as parallel and sequential lookup methods, which impact computational overhead and performance. We also discuss the scalability of our approach, which involves episode pagination, memory gisting, and interactive lookups, showing that the computational overhead scales linearly with input length, making our method efficient. Additionally, we evaluate ReadAgent's performance on various question-answering challenges without requiring model training, using LLM raters to assess exact and partial matches in responses. Section: Retrieval Augmented Generation, RAG. In this section, we discuss the concept of Retrieval Augmented Generation, or RAG for short. This technique is widely used to extend the amount of text that can be accessed beyond what a large language model, LLM, can hold in its immediate memory. We compare our ReadAgent to traditional RAG approaches that use standard methods to find relevant sections, or pages, in a lengthy text. Interestingly, we reuse the pages generated by ReadAgent for this purpose. We explore 2 methods for determining relevance: the Okapi BM25 and a neural retrieval method that relies on the Gemini API embedding model. For the neural retrieval, we calculate relevance scores by taking the dot product of the question's embedding vector with each page's embedding vector. In the case of the narrative QA dataset, we use what we call gist memory embedding vectors instead. When it comes to reading comprehension tasks, we rank the pages by how relevant they are to each question and then prompt the LLM to consider the top-ranked pages as context for answering the question. One challenge in retrieval is the sheer size of the document databases, which can make finding relevant information more difficult. However, both ReadAgent and the retrieval methods we discuss operate on a per-document basis rather than using the entire dataset, which simplifies the process. For instance, in the quality dataset, each article comes with several questions, and the database for each question includes only the pages extracted from that specific article, not the entire dataset. We also examine the use of full or truncated text content. For example, the longest articles in the quality development set contain around 6,000 words, which can fit within the context window of the PaLM-2L model. This allows us to directly compare ReadAgent's performance against using the entire document for comprehension tasks. However, for texts longer than the context window, such as those in the QM-SUM dataset, we truncate the text to ensure it fits within the model's memory, though this generally provides a weaker baseline. Additionally, we consider solving tasks by directly reasoning over a gist memory, which helps us understand the value of interactive lookup and how it compares to using full content and other retrieval methods. Focusing on quality, a multiple-choice question answering challenge, we note that the average length of the development set articles is about 4,122 words, with a maximum of 5,967 words. The gist memory, in contrast, averages 650 words in length. Our experiments show that ReadAgent, particularly when looking up 1 to 5 pages, performs best, even outperforming methods that use the full text. This suggests that current LLMs may struggle to effectively use large amounts of context, possibly due to training data limitations or the presence of distracting information. For narrative QA, which has the longest average context length among our datasets, we evaluate using both Rouge scores and LLM ratings. Due to the length of narrative QA texts, we significantly compress the text to fit within the model's context window. Our results show that ReadAgent outperforms all baselines across different subsets of narrative QA, demonstrating its effectiveness even with highly compressed text. Section Summary. In this section, we compare ReadAgent to Retrieval Augmented Generation (RAG) baselines using different retrieval methods to find relevant pages in long texts. We evaluate the performance of ReadAgent by ranking pages based on relevance to each question and prompting the large language model, LLM, to consider the top pages as context for answering questions. Our experiments show that ReadAgent outperforms using the full original text, indicating that limiting the context to a few relevant pages can enhance the LLM's performance in reading comprehension tasks. Section QM-SUM. In this section, we discuss QM-SUM, a dataset that includes transcripts from various meetings alongside questions or instructions related to them. We utilize a version of QM-SUM that has been put together by Scrolls, which stitches these transcripts together. These transcripts are notably lengthy, with their word count ranging from 1,000 to 26,300 words, and on average, they contain about 10,000 words. A visual representation of the distribution of word counts in the QM-SUM training set can be seen in a histogram we've included. The responses to the dataset's questions are in free-form text, leading us to use the Rouge F measure as the standard metric for evaluation. Additionally, we assess the results using our own LLM ratings. In our analysis, we've observed that the performance on the QM-SUM dataset improves as the compression rate decreases, meaning that methods which review more pages generally achieve better results than those reviewing fewer pages. Specifically, our ReadAgent S model significantly outperforms ReadAgent P and all other baseline models. This improvement, however, requires up to 6 times more requests during the retrieval phase. Given that such a marked performance improvement is not observed in other datasets, we believe that QM-SUM presents a unique challenge, likely due to the need for the model to sift through extensive transcripts to find pertinent information. This is plausible considering that meeting transcripts are inherently less structured than the documents, books, and movies found in other datasets like Quality and Narrative QA. A significant portion of tasks in QM-SUM involves summarizing rather than answering specific questions about the meeting content. In many cases, the LLM opts not to look up any pages, claiming it can summarize the entire meeting from memory. As a result, the average number of pages ReadAgent looks up is much lower than the maximum allowed. However, for tasks that do involve a question, ReadAgent tends to utilize most or all of the available lookup pages. When examining the Rouge scores, we don't always see a clear trend. This is because as texts get longer, which happens when compression rates decrease, the responses also get longer, leading to lower Rouge precision values and, consequently, lower F measures. For Rouge scores to improve with increasing text length, the gains in recall must outweigh the losses in precision. While this does occur to some extent, the effect is minimal. Moreover, including summaries, gists, in the text significantly increases response length across all read agent approaches, despite all models using the same question answering prompt. This complicates the task for GIST-MEM and read agent in surpassing retrieval methods in terms of Rouge score. Nonetheless, read agent S not only achieves the highest Rouge scores but also the highest LLM ratings. Given the limitations of Rouge, we find LLM ratings to be a more informative metric for comparing these runs. However, it's important to note that LLM ratings are not as straightforward to compare across different LLMs, such as GPT, nor do they facilitate easy comparisons with other studies. This observation is consistent with our findings from the narrative QA dataset. Additionally, we have conducted further ablation studies detailed in the appendix. In terms of retrieval quality, we compared using GIST-MEM with neural retrieval to look up one page against using read agent for the same task. Here, we found that replacing read agent's prompt-based retrieval with neural retrieval resulted in better performance by read agent's retrieval method.